we have Professor Frank Proske from Oslo, and he will speak about stochastic differential equation. Please.
Yeah. So thank you, Andre, for your introduction. Let me also thank you for the invitation. So I'm really pleased to participate in your seminar series. So as you can see from the title, so my talk is about well-posedness of the deterministic transport equation with singular velocity field perturbed along fractional Brownian paths. So in this talk today, I actually want to present a new result on so-called path-by-path uniqueness of stochastic differential equations driven by a fractional Brownian motion with a small Hurst parameter. And the proof of this result actually is based on methods of stochastic regularization theory, which is a rather recently established field of stochastic analysis. And after this, we will discuss an application of this result to the classical transport equation. Before we proceed with the presentation of those results, let me first recall and explain some previous results in connection with stochastic regularization theory in the case of a singular ordinary differential equation. So, you see. So let us first consider the first order ordinary differential equation here, which is driven by a vector field B. And as everybody knows, Picard iteration actually shows that there is a global, unique global solution if the vector field B here satisfies, for example, a linear growth and a Lipschitz condition. And then furthermore, if we in addition require that the vector field B here, so the driving vector field B here is k times continuously differentiable, then this regularity actually passes over to the flow of the associated equation. So that means that the interrelation between the initial condition and the solution itself for fixed time points is continuously, k times continuously differentiable again. But well-posedness here, so of the ordinary differential equation, so in the sense of Hadamard, that means in the sense of existence, uniqueness, and the regularity of solutions may fail if, as you know, the vector field lacks sufficient regularity. So for instance, if the vector field is not Lipschitz or discontinuous. So as we know, for instance, if the vector field is non-Lipschitz, then there may be not there may not even be a solution of our ordinary differential equation. So, but the situation actually changes dramatically. So if we cast a glance at the ordinary differential equation here, so if we integrate on both sides of this equation, and if we add to the resulting equation a small noise, say epsilon times Brownian noise, then we get, in fact, can you hear me? Yes, then we get, in fact, a stochastic differential equation here in this form. And we can see in this case that well-posedness of the ordinary differential equation can be restored. So more precisely, it turns out in this case that there exists unique global strong solution of this equation, regardless how small the epsilon in this equation is chosen, when B is just merely bounded and measurable. And this is a striking result which was found by Swantkin in 1974. So this can be in fact considered a milestone in the theory of stochastic differential equations. And then there are also some other papers, for instance, the paper of Very Katenikov, where this result was further generalized to the multidimensional setting. And then much later on, in 2013, there was a paper of Da Prato, Flandoli, Priola, and Rockner, who extended that result of Swantkin to the Hilbert space setting by using estimates of solutions to infinite dimensional Kolmogorov equations. And actually, moreover, if we denote by var phi st, the flow associated with the stochastic differential equation here, then it also turns out that the flow is a stochastic flow of Sobolev diffeomorphisms with respect to a weighted Sobolev space, when the driving vector field is just essentially bounded. And this is a result that was found by Salah Mohammed and co-authors in 2012. And as an application of this result, one can restore well-posedness of partial differential equations, say in this case of a transport equation with discontinuous velocity fields. So more precisely, one can construct a Sobolev differentiable unique weak solution of a stochastic transport equation of this form with a multiplicative noise, which is this term here, the noise term, which is given by a sum of Stratonovich integrals with respect to the independent Brownian components of the driving noise. And there have been also other papers in connection with the Sobolev differentiability or the regularity of the flow. There's, for instance, the paper of Fredrizzi Flandoli based on different techniques, PDE techniques. In the case of globally integrable vector fields, then there are other papers of Rezak Hanlu and also Aryasova and Pilipenko using completely different methods. And so now let us go back. Let us go back to this perturbed ODE, so this stochastic differential equation, and let us now consider a noise which is rougher than the Brownian noise here. So let us, for instance, replace the Brownian noise in the perturbed ODE by, for instance, a fractional noise with a small Hurst parameter. Then in this case, it turns out that we can observe, in fact, a stronger regularization effect of the ODE. So for example, if we assume that the vector field, the driving vector field is globally integrable and essentially bounded, so in the time homogeneous case, then one can find, in fact, a version of a solution whose flow is higher order differentiable if the Hurst parameter is small enough. This is a result obtained by Banyos and co-authors 2015. And it is somewhat surprising because it contradicts the paradigm that the flow inherits its regularity directly from the vector field, which is in our case ugly. There has been also other results in connection with strong solutions of SDEs driven by fractional Brownian motion. There's, for instance, a paper of Ley, a recent paper based on the so-called stochastic Ewing lemma, a topic which is linked to rough path theory. And there has been also previous papers, but in the one-dimensional case by Norbert and Ognin in 2002 and 3. So in the one-dimensional case. Before we proceed, let me also mention a tool, the main tool in the literature for the construction of unique strong solutions in connection with some previous results we have seen. This is, in fact, the main tool for the construction is the Yamada-Watanabe principle. For pedagogical reasons, let me just recall this principle. So if you have a weak solution and if you combine it with a pathwise uniqueness, then one obtains a unique strong solution. And strong solutions, as we know, strong solution, so which is a measurable functional of the deriving noise, is necessarily a weak solution, but not the other way around. And let me also recall the concept of pathwise uniqueness here. So say you have two weak solutions on the same probability space, say X and X tilde, say adapted with respect to possibly two different filtrations F and F tilde, then pathwise uniqueness implies that these two solutions, so X and X tilde, must coincide almost everywhere. And so papers or examples of papers based on this Yamada-Watanabe principle. This is, for instance, the paper of Junji Martinez from 2004, where the authors constructed a weak solution by using Skorohod's theorem and an estimate of Krylov, and then they combine it with pathwise uniqueness to obtain a unique strong solution. Then there also another paper, Junji Krylov from 1996. The authors there find a weak solution by using Euler's polygonal approximation, and again, an estimate of Krylov. Then there's another strong paper of Röckner and Krylov from 2005. Their weak solutions are constructed by using an argument of Portenko. And then let me also in this context mention some other methods which are not based on the Yamada-Watanabe principle. So there have been papers, so for instance, by Maya Brandes, Flandoli, Pilipenko and co-authors, which are based on Malliavin Calculus techniques. And there are also other papers in connection with strong solutions with respect to the fractional Brownian motion. So papers, recent papers of Ley and Cartellier-Gobinelli, but based on different techniques. So far we have looked at unique strong solutions of stochastic differential equations with discontinuous coefficients, and one may wonder here why this is reasonable, why one should do this. In fact, strong solutions with respect to stochastic differential equations with discontinuous coefficients have important applications. So, for instance, in the statistical mechanics of infinite particle systems, there, for instance, the stochastic dynamics of particles can be modeled by means of the so-called distorted Brownian motion with an irregular drift, and physicists here are actually interested in solutions which are measurable functionals of the physical process. So they're interested in strong solutions. And then there are also many important examples from stochastic control theory. There's a nice book on stochastic control theory written by Krylov. There you can find another examples. So in connection with the previous results, we have seen how we can, in fact, obtain well-posedness of solutions of ordinary differential equations by using probabilistic techniques. The question arising here is, and this touches the core of the talk today, is can we also use probabilistic techniques to study such equations in the path-by-path sense? Or in other words, can we employ probabilistic techniques to do a deterministic study of such equations? And a positive answer here is given by the following result, which in my eyes creates in some sense a bridge between the probabilistic world of stochastic partial differential equations and stochastic differential equations, and on the other hand, the deterministic world of partial differential equations and ordinary differential equations. And this is, in fact, a result which was originally conjectured by Krylov at the end of the 90s and proven by Alexander Davy in 2007. And in fact, Franco Flandoli actually claims that this result is one of the deepest results in stochastic analysis. And let me just state this theorem, which is due to Davy, Alexander Davy. So let us assume we have a Brownian motion, a d-dimensional Brownian motion, and a sample space given by the Wiener space, endowed with a Wiener measure. Then the STE, the following STE here, so driven by the Brownian motion, where B is a vector field which is merely essentially bounded, has a unique deterministic solution with respect to a measurable set of measure 1, which does not depend on the initial condition. So for each omega in this measurable set of measure 1, you can find a deterministic solution of this equation. So with respect to this specific Brownian path in the space of continuous functions. And the result is, so the proof of this result is quite complicated. And in the paper of Davy, based on the Markovianity of solutions of this equation, then some variational techniques and the use of the Borel-Cantelli lemma. And
Frank, can I ask you, it was a very old result of Krasnoselsky and Schussmann about such kind of...
Exactly, yes, yeah, you're right, yes. You're right, there are also some previous results in connection with Dussmann. Yes, based on it was first in the one-dimensional case and based on a transformation. But I think you cannot, in this case, consider discontinuous vector fields, as far as I remember.
Yes, exactly. It was a continuous vector field, but Let me ask you what is the main idea of this theorem of Davy?
Yes, it links. So you mean the consequences? So it links, in fact, to the deterministic world of ordinary differential equations. So that this result allows you to study ordinary differential equations, or in this case, the stochastic differential equations, which can be transformed into an ordinary differential equation in a deterministic way. So that means you fix a path of the Brownian motion, and then you can find a deterministic, unique deterministic solution to this equation in the space of continuous functions. So this notion is much stronger than the notion. So the notion of path by path uniqueness, it's much stronger than the notion of strong uniqueness.
Yes, I understand. Let me ask you the following question. In Krasnoselski result, it was some, at least in one dimension, it was a continuous mapping from the space of continuous function, which you consider as a noise, as a right part of the equation. And as a result of such mapping, we have a solution. If we substitute Brownian motion in those mapping, we get the solution with Brownian motion. But now let me ask you, in Davy's theorem, we have the statement which from the first look depend on the random process which we substitute there. For example, it is right for Brownian motion, and it can fail maybe if we substitute another process instead of Brownian motion, even with continuous path. Is it right?
Yes, this is true. I will then in a moment also give an overview of other results in this direction. So you may also, as you say, replace the Brownian motion by other types of noises. Yeah, you're completely right. And it's, let me also thank you for mentioning Sussman and Doss. So in connection, so they actually proved the first result in this direction. Yes, so you're completely right. But the vector field here was not discontinuous in their paper, and the first version was in for the one-dimensional case.
Yeah.
So the proof, as I said, is based on Malliavin. I have to switch on the light in my office. So sorry for that. It's switched off automatically after a while. So the proof of this result, which was conjectured by Krylov and proven by Davy later on, this is based on Markovianity, some variational techniques, and the Borel-Cantelli lemma. And later on, using then different techniques, and this is interesting, the proof was simplified by Alexander Shapovnikov and even improved in the following sense. So he could prove in 2016 in his first version, so of the paper, there exists an omega star of full mass, which does not depend on the initial condition. So in contrast to the previous result of Davy, so we have here a measurable set which depends on the initial condition. But then Mitnick, who refuted this paper, noticed that that actually the paper, the proof of Shapovnikov, even provides independence of the initial condition. And so then so let me state this theorem. So there exists a measurable set of full measure, not depending on the initial condition, such that for all such omega, our deterministic equation, so the STE for this specific path, has a unique solution in the space of continuous curves. So this is a further improvement of the paper of Davy, and based on different techniques which we actually exploit in connection with our results. Let me, before we proceed, let me mention some other results in this direction, but in a Markovian setting based on the techniques of Davy and Shaposhnikov. This is a result of Priola from 2018 in the case of stochastic differential equations driven by Lévy processes, special class of Lévy processes. Another paper of Budkowski and Mütnik. The authors establish path-by-path uniqueness in connection with a stochastic heat equation. And there's also another paper of Mütnik, also in the case of STEs driven by alpha-stable processes, even with coefficients which are distributional. And let me also mention a PhD work of Lukas Resch from 2017, where Resch could show path-by-path uniqueness in connection with stochastic evolution equations driven by a cylindrical Wiener process, which is quite astonishing in my eyes. But the techniques there rely on the techniques of Davy and exploit Markovianity heavily. So what is actually the objective of the talk here? So in this talk, I want to present an extension of the result of Davy-Shaposhnikov in the case of stochastic differential equations driven by fractional Brownian motion. So we replace the Brownian noise by a fractional Brownian motion where the Hurst parameter of the fractional Brownian motion is small, so between 0 and 1/2. Before we discuss this result, let me just for pedagogical reasons recall some facts about fractional Brownian motion. So here our fractional Brownian motion is a d-dimensional fractional Brownian motion consisting of components given by independent one-dimensional fractional Brownian motions. And what is the definition of one-dimensional fractional Brownian motion? Let me just recall this definition for convenience. So this is a one-dimensional centered Gaussian process, say BHT, on a probability space with a covariance structure given in this form, where the parameter here, H, called Hurst parameter, is between 0 and 1. And let me recall here some important facts or properties of fractional Brownian motion. So one can show that the fractional Brownian motion has a version which is locally Hölder continuous of any order strictly smaller than H. So that's why we have the notation H minus here. Then it is also known that it is a stationary and a self-similar process. So it satisfies this distributional relation here. And it has also some other properties which actually complicate the work with the fractional Brownian motion. This is in fact the property that the fractional Brownian motion is non-Markovian for H is not equal to 1/2, and it coincides with the Wiener process if the Hurst parameter equals 1/2. And another rather nasty properties that, or not very convenient properties, that the fractional Brownian motion is not a semi-martingale when H is not 1/2, so when the fractional Brownian motion is not the Wiener process. And let me mention another property, important property, which we heavily exploit, in fact, in connection with our results. And this is the property of strong local non-determinism of the fractional Brownian motion. So it's actually strong local non-determinism with respect to two sides. So the two-sided strong local non-determinism, which is this condition here, so this property here. And so this property, in fact, yields the interpretation that increments of the fractional Brownian motion are asymptotically independent in a local sense. So this is an interpretation of this property. Let me also finally mention that if the Hurst parameter is smaller than 1/2, the fractional Brownian motion can be written or represented as a stochastic integral with respect to a Brownian motion, B here, where the integrand here, KH, is the kernel, which is given in this form here. And you can, in fact, use the kernel here to represent the covariance function of the fractional Brownian motion. So we are coming now to the main result. So let us assume that our vector field B belongs to this space here. So in the time homogeneous case, that means that the vector field is globally integrable and essentially bounded. And let us assume that our Hurst parameter is small enough. So so smaller than this bound here, which depends on the dimension. Then we can find a measurable set of full mass, such so omega star, such that for all omega in this omega star, this equation here, so the stochastic differential equation here, has a unique solution in the space of continuous curves. So this is an extension of the result of Davy and Shapovnikov to the case of fractional Brownian motion. But before we carry on with the discussion of the idea of the proof, let me mention another result in this direction. So this is in fact a paper of Cartellier and Gubinelli, which dates back to 2016. And there the authors were even able to establish path-by-path uniqueness in the case of distributional coefficients in the Bezoff-Hölder space. But when the Bezoff-Hölder space is negative, so we are then in the distributional setting, then this integral here, which is in our case a classical integral, is given in terms of a nonlinear Young type integral. So this actually means that this result is not directly applicable to our case, so to the case of classical integrals when the vector field is essentially bounded, or in our class, so in the time homogeneous case, when the vector field is integrable, globally integrable, and essentially bounded. So you can actually not apply this result to our setting, and this has something to do with the discontinuity of the vector fields and the exceptional sets if you approximate, in fact, the vector field. So it's not applicable to our case. And there was also another result quite recently in March or April 2020 by Gagliati and Gubinelli. This is in fact a generalization of the techniques in the paper of Cartellier and Gubinelli. But also in this case, they cannot obtain this class of functions we are looking at in our talk now. So let me now come to the idea of the proof. The proof is based on on techniques in the paper of Alexander Shapovnikov, and this paper requires actually the verification of certain properties of the stochastic flow in connection with our stochastic differential equation, and some other techniques, some other arguments like the continuity theorem of Kolmogorov, and also the Borel-Cantelli lemma, plus some other arguments. But the most important arguments used are based on these certain flow properties. And the verification of these properties, in our case, relies on the following crucial estimate, which we prove in our paper. So if h is small enough, so smaller than this bound here, depending on the dimension, then, and let us assume we have a unique strong solution of our stochastic differential equation in this case, with respect to our vector field, which is globally integrable and essentially bounded in the time homogeneous case. And if you assume a compact cube and an R numbers, then for all S and all X and Y from that cube, we get this estimate here, uniformly in time. So where C is a constant depending on R, the dimension, the Hurst parameter, and the time horizon, and the cube, the compact cube. And in order to verify this,
Frank,
yeah.
Frank, maybe I missed something, but why we have the unique strong solution, at least for one initial condition?
Yes, you're completely right. It's actually a result which I present or recall at the end of the talk. So I should have.
So now we believe that it exists, yeah?
No, you have to believe, but you're completely right. Let me mention here that if B is from this class, so globally integrable and bounded, let us assume this, then one can show, in fact, that a unique strong solution to this equation exists. And this can be even further improved by other papers where the authors, for instance, so this is a paper of Ley, just assume that the vector field here is essentially bounded. But then I noticed some weeks ago that we can also use our techniques here to replace this space here, which we are looking at with respect to unique strong solutions, by the space of essentially bounded vector fields or functions. So okay. just to recall this result, but I will also, as you pointed out, I'm sorry for this, also mention this result at the end of the talk in connection with some additional properties.
Frank, I have a question. Tell me, please, when you say strong solution, you mean that X is adapted with respect to filtration generated
by the fractional Brownian motion. So in the traditional sense, not here in the sense of Davy, that means in the path by path sense, but only in the sense of a unique strong solution, in the traditional sense. So we are not looking here at this point at solutions which are unique in the sense of Davy. So we are just looking at unique strong solutions in this case. Okay. Mm-hmm. Okay, then we can show this estimate here, which is crucial in connection with the techniques in the paper of Shapovnikov. And in order to verify this estimate here, which is later on used in connection with the continuity theorem of Kolmogorov, and then also with Borel-Cantelli. We have to resort, or we need to resort to the following result, which is due to Frederic Vien and Vissara from 2007. This is a result which provides a supremum, a type of supremum concentration inequality of this form here, where n delta here is denotes the metric, that's classical metric entropy. And in our case, we apply this result to the case when the random field here in this assumption is given in terms of the derivative of our flow associated with the stochastic differential equation we are looking at. And in order to verify this assumption here, we in fact also have to prove the following result, which is matter of the next lemma, where we in fact show the following. So if our Hurst parameter is small enough, and if we, and let us assume that Bn is a sequence of vector fields compactly supported and smooth, which approximates our coefficient in our class of functions almost everywhere in this sense. And let us now assume we have denote by x as xn here, the unique strong solution associated with these approximating vector fields. So we are looking at strong solutions here. Then, in fact, if K is a compact cube in RD, then one can show that the following two sequences here. So the first sequence is with respect to the solution. The second here is with respect to the derivative of the flow. Then these two sequences are relatively compact in these spaces of continuous functions here respectively. But in order to prove this result, actually, one needs, or we at least resort to compactness criterion of Malliavin. So it's a compactness criterion for square integrable functionals of the Wiener process, which is based on Malliavin calculus, and which we apply to our solutions and the derivative of the solutions, in fact. But the derivatives of the solutions, so in fact, the second relative compactness statement is more demanding, can be proven by means of compactness criterion of D'Aprato, Malliavin, and Nuolat from 2092. So, which simply says, let me just recall this result. So let us denote by D12 the space of Malliavin differentiable random variables, and let us denote by D here, D in the definition of the Malliavin norm here, the Malliavin derivative in the direction of a Wiener process. And let us denote by H, and this is in our situation, the space of square integrable functions on the interval, say, from 0 to the time horizon T. And let us assume a self-adjoint compact operator C on our space H, the space of square integrable function in our case. Then it turns out that for all numbers C, real numbers C bigger than 0, the following set of Malliavin differentiable random variables is relatively compact in the L2 space. Here, C-1 denotes the existing inverse, because we assume here that this operator C here has a dense image. And this is a rather abstract formulation of relative compactness, and it's not very handy, but a more sufficient, so a sufficient and more handy criterion for relative compactness, which we in our case apply to our approximating solutions, is the following result, which is the result which is a consequence of the previous result here, is the following lemma. So if we fix a time t in our interval, and if we assume a beta between 0 and 1/2, and if we assume that this condition and the other condition in terms of a fractional integral exist, so where d here, in fact, denotes the Malliavin derivative in the direction of the Brownian motion in the stochastic integral representation of the fractional Brownian motion. As you may remember, we have a stochastic, we can represent the fractional Brownian motion as a stochastic integral with respect to a Wiener process and with respect to a kernel, which is the integrand. So then it turns out that these approximating solutions for each fixed time point are relatively compact in our L2 space. So in order to get a feeling for the verification of these conditions, let me explain how we obtain these estimates for the expressions here in the lemma. So and how we can show, in fact, the first relative compactness statement in this result here, where we approximate our vector field. So how can we, in fact, verify these two conditions here? We can, in fact, apply the Malliavin derivative in the direction of the Brownian motion to both sides of this equation. So the stochastic differential equation here for the approximating coefficient Bn. And if we combine this with the chain rule for the Malliavin derivative, we get a linearized equation of this form in terms of the Malliavin derivative, where the prime here, so B prime n, stands for the derivative, the spatial derivative of the coefficient, and where kh is the kernel in the stochastic integral representation of the fractional Brownian motion, and ID is the unit matrix. So if we use here Picard iteration, we can find a representation of the Malliavin derivative in terms of a sum of n-fold iterated integrals in this form here, where the convergence is in the LP space. So now if we use Gazanov change of measure and the next step, we can in fact replace the approximating solutions sitting in these coefficients here in the integral by a translation of the fractional Brownian motion at the corresponding time points on the simplex. And then we can in fact represent each of these n-fold iterated integrals here. So in the representation of the Malliavin derivative, in this as an integral of a deterministic function depending on time on the simplex times the partial derivative d alpha of a smooth, compactly supported smooth function f of the fractional Brownian motion on, so this is the fractional Brownian motion on the simplex. And then in the next step, in order to get rid of the derivatives here in the n-fold iterated integral, we apply in some sense a local time variational calculus argument. And then we can represent such an integral here in the sum in this form here, namely as an integral in terms of an integral of the function f times the partial derivative of the local time of the fractional Brownian motion on the simplex. So you have to remember here that if the Hurst parameter is small enough, we actually have a local time in the case of a fractional Brownian motion. This is not, as we know, the case with the Brownian motion. And so here we also use, in fact, an occupation type formula of this form here. So L kappa n denotes here the local time of a fractional Brownian motion on a time simplex. So this time simplex. So in order then to verify these conditions here in our compactness criterion, we also need some control, in fact, in this integral of the partial derivative of the local time. So we need an estimate, a uniform estimate, a moment estimate with respect to this random field here in the integral. And this is in fact provided by the next result, where we obtain a uniform second moment, uniform estimate with respect to the second moment, so of this form with an upper bound in terms of a function or an expression phi, which is given as a sum of these integrals here with respect to so-called shuffle permutations, which is a concept which is used sometimes in rough, for instance, in rough path theory. So with this estimate in hand, we can finally verify these conditions here, and combined with an Arthur-Ascoli argument, we can show relative compactness of this sequence here in the space of continuous functions. And we can apply similar arguments to the case of the derivative of the flow, but this is much more, this actually necessitates much stronger efforts in this case. So, but I wanted to give you some feeling how we proceed in our proof based on the relative compactness criterion. So now, finally, let me discuss application to the classical transport equation. So, so let us consider this partial differential equation here, so referred to as classical transport equation, with an initial condition U0. And in fact, if we require that the velocity field here, or the vector field B here, is locally Sobolev differentiable and satisfies the three conditions here, also in terms of the divergence of B. So it's not really a divergence operator, as I can see here. So I didn't apply a direct command for the divergence operator here in my TeX file. So excuse me for that. So if we assume that these three conditions are satisfied, then it was proven in a striking work, in fact, by Diperna and Lyons in 1989 by using the so-called concept of renormalized solutions, that the transport equation here has a so-called unique weak solution in this class here of functions. So in this L1 class of functions. So what does weak solution here mean? So weak solution here means that the solution satisfies an equation which is obtained by integrating our classical transport equation against test functions. Then you obtain a weak form of your classical transport equation, and this means a weak solution. In fact, here existence, let me just mention this, is, as you know, not an issue here, because existence can be rather obtained in an easy way by using a simple weak compactness criterion. So the issue here is, in fact, uniqueness, that you obtain uniqueness. And let me also mention here some counterexamples. So for instance, in the one-dimensional case, if we consider a vector field B of this form here with the sine function, then one can directly verify, so then one sees that the vector field is locally Sobolev differentiable and is in this class of functions here. But the other two conditions in the paper of Deterministic, so these two conditions here are not satisfied. So they're violated. And it turns out that in this case, the transport equation doesn't allow for a unique weak solution. So in this case, we have in fact infinitely many solutions. And other counterexamples are provided by our class of functions. So if we choose irregular vector fields B from our class, so L1 infinity, so this notation here, which stands for, as I mentioned before, for globally integrable vector fields, which are essentially bounded in the time homogeneous case. So then in this case, we also see that that uniqueness fails in connection with vector fields taken from this class of functions. So what can we do in fact here? What can we do here to restore well-posedness of our classical transport equation when B is globally integrable and essentially bounded, so irregular in this sense. So what can we do in this case? So we could, for instance, restore well-posedness. So this is what we are aiming at by replacing in our transport equation here the velocity field B by a perturbed velocity field in this form. So a velocity field which is perturbed from the inner along a fractional Brownian path. So we may also consider here, if you want, a path, a small path, in the sense, a small perturbation in the sense that we replace the fractional path by epsilon times the fractional path. So then we consider, in fact, instead of this equation here, a perturbed equation, so with the perturbed velocity field of this form. And we can, in fact, show by using our previous result on path-by-path uniqueness of STEs the following result. So if B in the time homogeneous case is globally integrable and essentially bounded, and if H is small enough, so with a bound here for the Hurst parameter given by this expression, the minimum of these two numbers here, and if you assume that the initial condition U0 is K times continuously differentiable with bounded partial derivatives of all orders, and P is bigger than the dimension, and K bigger than 2, then if we replace in our transport equation the vector field B by this vector field here, or if you again, if by a vector field where you consider instead of BTH epsilon times BTH. Then there exists a measurable, a set of full measure, such that for all omega from that set, there exists a unique weak solution. In this class of functions here, of Sobolev differentiable functions, and moreover, we have some spatial regularity. It turns out that for each fixed t, our solution is k times weak Sobolev locally Sobolev differentiable.
Frank, and does this imply that U is continuously differentiable with respect to X by Sobolev theorems?
What did you say? Excuse me?
Is it true that a function U is continuously differentiable in X? Is it possible to apply Sobolev embedding theorems?
Yes, of course. Yeah, so you can find in this case then k times a continuously version, differentiable version. Yes.
Maybe k minus 1.
Yes, if p is big enough. So here in our case, p is bigger than d, but in fact, since you are dealing here with essentially bounded vector fields, we can choose this p as high as we want. So let me say something about the proof. So the proof, as I mentioned, is based on the path-by-path uniqueness of solutions, which we previously obtained, the method of characteristics, and the following result, which I announced earlier in connection with the comment of Andre. So if our vector field B is globally integrable and essentially bounded, and if H is small enough, so depending on the dimension and the degree of differentiability K, then there exists a unique global strong solution of our stochastic differential equation driven by the fractional Brownian motion. And moreover, it is Malliavin differentiable in the direction of the Brownian motion and the stochastic integral representation of the fractional Brownian motion. And we can also find that this associated flow is k times locally Sobolev differentiable. So, or more precisely, regular in this sense. And finally, let me mention a related recent work in connection with this result here on the transport equation. This is a result from March 2000, or it was April 2020, of Gagliati and Gobinelli. They, in fact, also obtain such a result here at the end of their paper, but for continuous coefficients, so continuous velocity fields B. So actually their techniques cannot be applied to our situation. So finally, let me give an overview here of the papers I have mentioned in connection with this talk. So for instance, a paper of Ambrosio, which extends a result of Diperna and Lyons, which deals with vector fields which are in the space of bounded variation functions. Then we have a paper of Ariaso and Pilipenko on differentiability of stochastic flows, so a method which is very nice but completely different from our method here. Then there are also some other methods. The paper of Mütnik in connection with path-by-path uniqueness in the case of the stochastic heat equation. Then the paper of Cartellier-Gobinelli I mentioned before, where they establish the author's path-by-path uniqueness, even for distributional coefficients. Then there is the compactness criterion of da Prato, Malliavin, and Norbert. We were using then this paper, which in fact Franco Flandeli considers one of the breakthroughs of stochastic analysis, the paper of Alexander Davy. Then we have the paper of Lyons, and then of Junji, all the papers I mentioned, connection with strong solutions, and also the book, of course, of Portenko, which is the classical book everyone should use, and then also the paper of Shaposhnikov from 2016, which is an improvement of the paper of Davy. So thank you for your attention. So excuse me for the delay.
Thank you very much for interesting and detailed explanation. And I think that participants will have a question, please. Maybe comments.
Frank, could you please explain one more time, why do you have uniqueness when you solve equation in a Davy sense? You considered approximation Bn converges to B, and processes Xn converge to a limit.
Yes, from that alone, you won't get uniqueness in the sense of Davy. But you have to combine it. Let me go back to this result you are referring to. So you mean this result, the lemma? Yes. Yeah, of course. So we use this result to verify the assumptions of the result of Frederick Guin, which provides this supremum concentration type of inequality. And this is actually which we use to prove this estimate here. And this estimate here is very central in the paper of Shaposhnikov. This estimate here.
But these solutions are strong solutions, not
strong solutions. Exactly. Yes. And the paper of Shaposhnikov rests on certain properties of the flow, and the verification of these properties requires such an estimate. So in the Markovian setting, such an estimate, as he mentioned in his paper, is obtained by using PDE techniques. But here we use a different technique based on the paper of Vien and also a compactness criterion. And then if we combine these properties with some other arguments in the paper of Shaposhnikov, which do not rely on Markovianity, so they do not rely on Markovianity, only the verification of this estimate here, this estimate, and some other estimate, but the other arguments do not rely on Markovianity. And this is why the paper of Shaposhnikov is quite strong. So this was noticed by Mitnick. So he noticed, in fact, there are several aspects which makes this paper so interesting. So compared to the paper of Davy. And to be honest, in the course of writing this paper with my colleagues, I have not been able to develop an intuition. So a clear intuition, intuition cannot be always very clear, but a good intuition for which properties are needed to get path-by-path uniqueness. If you, so this is not, so the only intuition is, if you cast a glance, if you cast a glance at the paper of Shaposhnikov, which is quite technical, is that you need certain tail distribution properties to be able to use Borel-Cantelli, the lemma of Borel-Cantelli, in a certain way. So this is the only intuition I developed. But honestly, I have no real intuition for this problem. So it's quite technical. The intuition I can see comes from the tails of the distribution, which enables one to apply the Borel-Cantelli lemma in a certain way.
And one more question about uniqueness for transport equation. Do you consider inverse flow? So is it a way?
Yes, exactly. I consider the method of characteristics, which requires the inverse flow. So the transformation applied to the inverse flow. And then the application of the classical chain rule, which is rather limited in the Sobolev case, as you know. So we increase in some sense the regularity of the flow to be able to use classical tools from analysis.
I see.
So in fact, you could also say, yeah, why haven't you looked at the corresponding stochastic transport equation, which with a noise outside? So we could have also looked at the stochastic transport equation with a multiplicative noise in terms of stochastic integrals, so Stratonovich integrals. And in this case, in fact, this is also possible, as I mentioned before, in connection with the Wiener process. But the issue here, as I mentioned before, is uniqueness. And uniqueness in the Wiener case is obtained by using the Ito-Wenzel formula. And if you apply here the fractional Brownian motion, first you have to give a meaning to the stochastic integrals involved, maybe in terms of a rough path integral, but then you need higher regularity with respect to your velocity field on the other hand. But in this case, Ito's lemma is quite complicated to apply. And in my eyes, it's also not very natural to have a multiplicative term, noise term, because it's rather far away from the original equation.
Thank you.
Okay, some other questions, please. Frank, I have several questions. Firstly, usually when we can calculate or estimate stochastic derivative, we can say something about existence and properties of density, probability density of the solution. Do you have such results in this case?
This is a very good question. Yes, unfortunately, we have actually never looked at this case, but thought about that. It could, let me see. It is, but then you need control on your Malliavin matrix, which requires very good estimates. I'm not sure in this case whether we can manage to do so, but this is a very interesting question to look at.
Okay, the next question is about the mapping which you actually establish from the set of trajectories of the noise to the set of trajectories of the solution. Actually, you claim that on the set of probability 1 of such trajectories, you have a mapping which maps the noise into solution. And what will be the properties of this mapping? As we see in your talk, you get some claims about the stochastic differentiability of the solution. It means that you know some properties of this mapping. But if we will back to original results of Schussmann, Krasnoselsky, then we know that in those cases, those mapping was continuous or have some another good properties. Now, can you say something about this mapping from space of trajectories of this fractional Brownian motion to the space of solution?
So you mean in some sense the Ito map?
Exactly.
Yes. This is a very good question. So since we in addition since we can in addition say or obtain some other regularity conditions, regularity properties, it could be plausible that the Ito map also exhibits some nice properties. You're right, but I cannot directly see, just as in the case, say, for instance, of Sussman, how we can say something about this Ito map. So, but it's plausible. You point at something interesting. So it is quite plausible that you could show some nice properties of this map. But we haven't done so far, but it's quite plausible.
Also, the last question is the following. In 1998, I introduced such class of Gaussian process, Gaussian integrators. These are Gaussian processes which are like result of application of conditional expectation to Brownian motion. And this process in general case have the local non-deterministic property allows to say that this process have a local time, so and also have a good kernel representation with respect to Brownian motion. So I think that the class of the noises can be essentially extended.
Yeah, it also seems to me, and I think it must be then not only a strong local non-determinism alone, but a strong local non-determinism from different directions. So actually in our papers, so also with Andrei Pilipenko, we exploit a two-sided strong local non-determinism, which was quite important. So if you want to extend this result to the multi-parameter case, I think it should be possible, for instance, for fractional Brownian motion proposed by Zhao on the torus. So where you have this property from all directions, the strong local non-determinism.
Yes, there are a lot of papers in this direction. For example, Yimin Yao, which also proposed a lot of concepts of local non-determinism for random fields.
But this is very interesting. I think you're completely right. So, and I remember you also mentioned that once we discussed this issue some years ago, and I think it's quite promising to have a look at your paper. So I'm quite optimistic that this could be done.
Okay, I will send to you.
In view of the papers of Gobinelli, so a series of papers of Gobinelli.
Okay, Frank, so some other questions or comments? If there are no other questions, thank you very much, and hope that this is not your last talk at our seminar.
It was a big pleasure for me. Big pleasure for me to participate in your seminar series.
Okay, so we stop it for today. Thanks, everybody. Bye.
So wish you Merry Christmas, although Christmas in your case is next month.
Yes, in next month, but
we also celebrate Catholic Christmas. It's official holiday.